Okay, so the generalized design flow includes the present states and the inputs, and so we have to decide for the flip-flop type, the SRJKT, then they have to be mapped, and then we have to derive the input equations. So once we got the next states, actually, from the flip-flops based on the flip-flop equations, we need to have extract the excitation tables from the characteristic equation of the flip-flops. And these excitation tables are actually going to give us the flip-flop inputs. And then we can use these and the K-maps and optimize the flip-flop inputs. So we need to modify the design procedure after the state reduction and state assignment steps in order to handle different types of flip-flops. And what do we need to do? Plot the next state K-maps for flip-flop outputs, like we have done it. Transform next state K-maps to flip-flop input maps. For a D-type flip-flop, this is pretty straightforward. For the other flip-flops, we have to derive the input equations. And in order to derive input equations, we have to use excitation tables. And then we have to simulate and build like we have done it in the previous examples. Okay, so let's try another example, which we will talk about a counter design. A 3-bit counter with asynchronous reset. Initial state is 0, 0, 0. So all these are given. There are no inputs over here. So it's just a counter. And in order to implement this counter, I'll start with a simple state diagram 0, 0, 0, 0, 0, 1, then 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So it goes from one state to the other based on the clock tick. So whenever the clock is changing, we are changing the state. We are counting up. And its wraparound means when it reaches to 1, 1, 1, it goes back to 0, 0 and starts again. Now, this is pretty straightforward, but we have to understand, is this Mealy or Moore model? Now, one thing that we need to see over here, as there are no inputs and the states are changing based on the clock, we can easily say that this is a Moore model. And there are no outputs, okay? It's because the outputs are actually the same as the states. There's nothing different over here. Okay, so let's derive the state table. Everything is pretty clear over here. Now, we have got from this state diagram, we can easily see that we have got 8 states. In order to cover all 8 states, we need 3 flip-flops. A, B, C. No input, A plus, B plus, C plus, and no outputs. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1 to cover all 8 states. Okay. So 0, 0, next state is 0, 0, 1, then 2, then 3, 4, 5, 6, 7, 8, and wraps around. This is the state table that we are going to derive. Now, let's implement this counter by using T-type flip-flop, because so far we have seen two examples that we have used D-type. Let's use T-type. But before we get into it, I have to introduce something else now. What do we know about T-type? Let's just revise it. So we have said that the next state of the T-type is T XOR Q. And the symbol is given as. Now, the characteristic table that we have derived the equation from it is telling us 0, 0, 0, 1, 1, 0, 1, 1, that when t is 0, next state is the present state. When t is 1, it's inverted, it's toggling. This is known as characteristic table. Now, in order to derive the flip-flop inputs, we also need excitation table. This is something that we introduce now, and it's quite important. Excitation table is just like a mirrored or opposite version of the characteristic table. So we have got inputs as the present and the next, and the output as t. So we are going to look at the relationship between the present and the next states so that we can derive the flip-flop value. So for example, for the T-type flip-flop, when present is 0, next is 0, it means that T is not affecting the next state. T is not 1, so that the next state is changing or toggling. So it's just following the present state. So I can say that at this point, T is 0. Present is 0, next is 0. So you can see that it's toggling. Toggling means T has to be 1. 1, 0, it toggles again, so it has to be 1. 1, 1, it holds. So the excitation table of T-type flip-flop is exactly the same as the characteristic table. Okay, so there is nothing different over here, only for T-type flip-flop. So if we put those down as well, you can see the excitation table. And we just need to extract the relationship between the present and the next states, and then the T inputs of the flip-flop. So once we have got this, if I go back to the table, I can over here say TA, TB, and TC, because we are going to use those and find out the relationship between them for each of the present and the next states. Okay, let's see how this is going to be done. Now, if we look at it, let's start with A. Present is 0, next is 0. Toggling? No. Present is 0, next is 0. Toggling? No. 0, 0, no. 0, 1, toggles, yes. 1, 1, no. 1, 1, no. 1, 1, no. And 1, 0, toggles. Then B. We go to B. 0, 0, no. 0, 1, toggles. 1, 1, no. 1, 0, toggles. 0, 0, no. 0, 1, toggles. 1, 1, no. 1, 0, toggles. And the last one, 0, 1, toggles. 1, 0, toggle. 0, 1, toggle. 1, 0, toggle. 0, 1, toggle, 1, 0, toggle, 0, 1, toggle, and 1, 0, toggles. So we have got TA, TB, and TC. Now, all I need to do is I have to derive a K-map for each of these. so that I can optimize the input equation for each of these flip-flops. So we need 3 K-maps. I'm gonna fit everything over here. 3 variable, 8 states. A, B, C, A, B, C, A, B, C, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, and 0, 1. Okay, so let's fill out the tables now. Okay, so 0, 0, 0, 1, 0, 0, 0, 1, and then 0, 0, 0, 1. Okay, so 0, 0, 0, 1. This is the first one. Then let's do B as well, then we can derive the equation. 0, 1, 0, 1, 0, 1, 0, 1. Okay. 0, 1, 0, 1, 0, 1, 0, 1. And then C is all ones. So 1, 1, 1, 1, 1, 1, 1, 1. Okay. Now the equations, so these two, which is TA is equals BC, TB equals C, and TC, as you can see, all are combined, which is equals 1. Now we have got the expressions for the flip-flop input equations. Then all we need to do is throw it. So T, 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 let's say A, B, C, clock, 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 Q, Q bar, Q, Q bar, Q, and Q bar. All the clocks are combined. So BC, this is coming from B and C. And then we have got C, which is coming from this one. And we have got 1. So this is straight 1. That's all. So we have got the circuitry which implements the counter design. And we can easily see that. You can also do the next state maps and the flip-flop inputs. It doesn't matter, or you can just directly come from the truth table, the state table, by putting all the states down there. So the logic diagram is similar to what we have implemented. It's just a horizontal version of it. And you can see that if you want to have a asynchronous reset, you can have the reset. When the reset is activated, none of the inputs or outputs are going to change. And when reset is 0, then we have got the operation.